Bismillahirrahmanirrahim and hello everyone. Now I would like to share about topic 7, oscillation and wave. In this session you have topic 7.4, properties of wave, 7.5, superposition of wave, 7.6, application of stationary wave, and 7.7, Doppler effect. With me, Madam Heria. Before we go further, let's look the learning outcome of what you should emphasize in this subtopic. 7.4, properties of wave. 7.5, superposition of wave. 7.6, application of stationary wave. And 7.7, Doppler effect. Sinusoidal wave parameters. Figure 7.4 show a periodic sinusoidal waveform. Amplitude consists of crest or peak, which is maximum amplitude, and trough, which is minimum amplitude. From the figure 7.4, we can see particle B is in phase with particle C. Particle P is in phase with particle Q. And particle S is in phase with particle T. Wavelength, lambda, is a distance between two consecutive particle points which have the same phase in a wave. The SI unit of wavelength is meter. Include in learning outcome. Periodic T is the time taken for a particle point in the wave to complete one cycle. Its unit is second. In this period T, the wave profile moves a distance of one wavelength lambda. Thus, period of the wave equals to period of the particle on the wave, and T equals to 1 over F. Frequency F is the number of cycle wavelength produced in 1 second. Its unit is hertz or per second. Amplitude A is the maximum displacement from the equilibrium position to the crest or trough of the wave motion. Wave speed V is the distance traveled by a wave profile per unit time, as in figure 7.5. It is moved a distance of lambda in time t, hence V equals to distance over time, V equals to lambda over t, and t equals to 1 over f. So V equals to f lambda. The SI unit of wave speed is meter per second. Wave number k is defined as k equals to 2 pi over lambda. The SI unit of wave number is per meter. Include in a learning outcome. Displacement y is the distance moved by a particle from its equilibrium position at every point along a wave. Equation of displacement for sinusoidal progressive wave. From figure 7.6, for graph y, again x, you can see amplitude and point O and P. Consider x equals to 0 as a reference particle. The equation of displacement for particle at x equals to 0 is y equals to a sine omega t. The general equation of displacement for sinusoidal progressive wave is y equals to a sine omega t minus kx plus phi if the wave propagates to the right. y equals to a sine omega t plus kx plus phi if the wave propagates to the left. Include in a learning outcome. We must know where y equals to displacement of the particle as a function of x and t, a is amplitude of the wave, omega is angular frequency, k is wave number, x distance from the origin, t is time, and phi is phase angle. Displacement graph of the wave. From y equals to a sine omega t plus minus kx plus phi, the displacement y varies with time t and distance x. Graph of displacement y against x. The graph shows the displacement of the particles in the wave at any particular time t. For example, if you have graph y equals to a sine omega t minus kx, at t equals to 0, substitute t equals to 0 in the equation, mathematical solution, so y equals to negative a sine kx. Include in learning outcome. Graph of displacement y against t. Is the graph show the displacement of any one particle in the wave at any particular distance x from the origin. For example, if you have graph y equals to a sine omega t minus kx, for the particle at x equals to 0, substitute x equal to 0 in the equation, so y equals to a sine omega t. This is graph y equals to a sine omega t. Included in learning outcome. Equation of a particle's velocity in wave. If you have graph y equals to a sine omega t plus minus kx, apply Vy equals to dy over dt. Differentiate the equation, mathematical solutions. So Vy equals to a omega cos omega t plus minus kx, where Vy equals to velocity of the particle in the wave. Include in learning outcome. The velocity of the particle Vy varies with time, but the wave velocity v is constant. Thus, Vy not equal to v. Equation of a particle's acceleration in wave. From previous equation, Vy equals to a omega cos omega t plus minus kx. Using ay equals to dvy over dt, differentiate the equations. Finally, you got ay equals to negative a omega squared sine omega t plus minus kx, where ay is acceleration of the particle in the wave. The equation of the particle's acceleration also can be written as ay equals to negative omega squared y. Means the vibration of the particles in the wave executes as hm. The difference between particle vibrational velocity and wave propagation velocity. Include in learning outcome. Particle vibrational velocity equation is Vy equals to a omega cos omega t plus minus kx, whereas wave propagation velocity is v equals to f lambda. Particle vibrational velocity is velocity of the particles in the wave and varies with time. But wave propagation velocity is a distance traveled by a wave profile per unit time, and it's constant. Superposition of wave. Principle of superposition. State that whenever two or more waves are traveling in the same region, the resultant displacement at any point is the vector sum of their individual displacement at that point. Include in learning outcome. Example. Interference is an interaction or superposition of two or more wave motion. For constructive interference, if the resultant displacement is greater than the displacement of the individual wave. From the graph, y1 and y2 is individual wave, whereas y is a resultant displacement. It occurs when y1 and y2 have the same wavelength, frequency, and in-phase each other, where delta phi equal to 0, 2 pi, 4 pi, 6 pi, 8 pi, and so on. Destructive interference is the resultant displacement is less the displacement of the individual wave or equal to 0. From the graph, y1 and y2 is individual wave, whereas y is a resultant displacement. It occurs when y1 and y2 have the same wavelength, frequency, and antiphase or out of phase pi radian each other, where delta phi equals to pi, 3 pi, 5 pi, 7 pi, 9 pi, and so on. Standing or stationary wave is a form of wave in which the profile of the wave does not move through the medium. It is formed when two waves which are traveling in opposite direction and which have the same speed, frequency, and amplitude are superimposed. As figure 7.5. Note N is a point at which the displacement is 0, where the destructive interference occurred. Antinode A is a point at which the displacement is maximum, where the constructive interference occurred. Characteristic of stationary wave. Nodes and antinodes appear at particular time that is determined by the equation of the stationary wave, as figure 7.6. The distance between adjacent nodes or antinode is lambda over 2. The distance between a node and an adjacent antinode is lambda over 4. Therefore, lambda equals 2 times the distance between adjacent nodes or antinodes. Equation of stationary wave. Consider you have two waves, y1 equals to a sine omega t minus kx, y2 equals to a sine omega t plus kx. By applying y equals to y1 plus y2, mathematical solution, so y equals to 2a sine omega t cos kx. Finally, you got y equals to 2a cos kx sine omega t, where 2a is amplitude of the standing wave or new amplitude, a is amplitude of the progressive wave. Include in a learning outcome. Explanation for the equation of stationary wave y equals to 2a cos kx sine omega t. A is new amplitude. A cos kx determine the amplitude for any point along the stationary wave. It is called the amplitude formula. Its value depends on the distance x. For antinodes, the point with maximum displacement equals to a. A cos kx equals to a. Mathematical solution. Therefore, antinodes occur when x equals to 0, lambda over 2, lambda, 3 lambda over 2, and so on in unit meter. Notes, the point with minimum displacement equal to 0. A cos kx equals to 0. Mathematical solution. Therefore, nodes occur when x equals to lambda over 4, 3, 4, lambda over 4, 5 lambda over 4, and so on in unit meter. For sine omega t is to determine the time for antinodes and nodes will occur in the stationary wave. Antinodes, the point with maximum displacement equals to a. If you have equation A sine omega t equals to A, mathematical solution, therefore antinodes are occur when the time are t equals to t over 4, 3 over 4, 5t over 4, and so on. Unit is second. Note the point with minimum displacement equals to 0. If you have equation A sine omega t equals to 0, mathematical solution, therefore nodes are occur when the time are t equals to 0, t over 2, t, 3 over 2, and so on. Unit in second. At time t equal to 0, all the points in the stationary wave at the equilibrium position y equal to 0. Graph of displacement at distance y again x. You can see the antinode and nodes of the graph. The difference between progressive and stationary wave include in learning outcome. Progressive wave have wave profile move and all particles vibrate with the same amplitude, whereas standing wave is wave profile does not move particle between two adjacent nodes vibrate with different amplitudes. In progressive wave, neighboring particles vibrate with different phase. All particles vibrate produced by a disturbance in a medium and transmit the energy. But in standing wave, particles between two adjacent nodes vibrate in phase. Particles at nodes do not vibrate at all and produced by the superposition of two waves moving in the opposite direction and does not transmit the energy. Application of stationary wave. Wave on a straight string. Wave speed on the string. The equation of the wave speed on the string is given by v equals to t over mu, where v equals to wave speed on the string, t is tension in the string, mu is mass per unit length on the string. Include in learning outcome. SI unit for t is Newton and mu is kg per meter. The value of mu is obtained by using two methods. One, if the length of the string is L and its mass m, thus mu equals to m over L. 2, if the radius of the string is r and its density rho, thus mu equals to rho a, where a is cross-sectional area, or mu equals to rho pi r squared. Include in learning outcome. Vibrational modes on a string fixed at both ends. When a string is plucked, a progressive transverse wave is produced on the string. This wave is traveling to the both fixed end incident wave and a reflected wave as shown in figure. The superposition of both waves making stationary transverse wave and the simplest pattern of the stationary wave on the string is shown in figure. Include in learning outcome. The stationary wave on the string forces the air vibrates and produces a sound wave in the air. If the string vibrating in the fundamental mode, hence the sound wave produced in the fundamental tone. Therefore, F0 sound wave equals to F0 string vibration. The phenomenon is called resonance. What is meant by resonance? Is defined as the phenomenon of the occurrence of a maximum amplitude when the driving frequency equals the natural frequency of a system forced into oscillation. Table 7.1 shows the harmonic series on a string fixed at both ends. Fundamental first harmonic, first overtone second harmonic, second overtone third harmonic. So in general, f equals to n over 2l square root t over mu. So fn equals to nv over 2l, or f equals to n f0, where n equals to 1, 2, 3, and so on. Example of vibrational mode is a string fixed at both ends for musical instrument, a piano, violin, and a guitar. Include in learning outcome. Wave in an air column for closed pipe. or a column with one end closed. If the air in a pipe that is closed at one end is disturbed by a source of sound, example tuning fork, a progressive longitudinal wave travels along the air column and is reflected at its end to form a stationary longitudinal wave is shown in figure. The simplest pattern of the stationary wave was produced have the nodes and the closed end while the antinode is at the open end as shown in figure. When the frequency of the tuning fork coincides with the fundamental frequency F0 of the air column, a resonance takes place. A sound of high intensity is produced at this frequency. Table 7.2 shows the harmonic series in an air column with one end closed or closed pipe. Fundamental, first harmonic, first overtone, third harmonic, second overtone, fifth harmonic. So in general, Fn equals to Nv over 4L or F equals to Nf0, where N equals to 1, 3, 5, odd numbers. Only odd harmonics are allowed in vibrational modes of an air column in closed pipe. Example of vibrational modes and air column in closed pipe for musical instrument is clarinet. Include in learning outcome. Open pipe or air column with both ends open. If the air in an open pipe, both ends are open, is disturbed by a source of sound, example tuning fork as shown in figure, a progressive longitudinal wave travels along the air column. This wave will superpose with another progressive longitudinal wave produced by the air outside the pipe and form a stationary longitudinal wave. The simplest pattern of the stationary wave was produced have the antinode and both open end while the node is at the middle of the pipe as shown in figure. If the frequency of the tuning fork equal to the fundamental frequency F0 of the A column, resonance takes place. A sound of high intensity is heard at this frequency. Table 7.3 show the harmonic series in an air column with both ends open or open pipe. Fundamental, first harmonic, second overtone, second harmonic. Sorry, first overtone, second harmonic, second overtone, third harmonic. So in general, Fn equals to Nv over 2L or F equals to Nf0, where N equals to 1, 2, 3, real numbers. All harmonics are allowed in vibrational modes of an air column in open pipe. Example of vibrational modes and air column in open pipe for musical instrument are flute and recorder. Include in learning outcome. Sound intensity is the rate of sound energy flow across unit area perpendicular to the direction of the sound propagation, or I equals to E over TA, or I equals to P over A. So I equals to P over 4 pi R squared, where I is sound intensity, E sound energy, A area perpendicular to direction of sound propagation, T time, and P sound power. It's a scalar quantity and unit is watt per square meter. Doppler effect is defined as the change in the apparent observed frequency of a wave as a result of a relative motion between the source and the observer. Stationary source and observer. Any source of sound emits sound wave to all directions with same speed and produce spherical wavefront as shown in figure. Whereas source of sound O observer, V speed of sound, lambda wavelength of the sound wave, F source or true frequency, Fa is apparent or observed frequency. Whereas wavefront is defined as a line or surface in the path of a wave motion on which the disturbance at every point have the same phase. Equation of Doppler effect in general, Fa equals to Fa equals to V plus minus V naught over V minus plus Vs times F, where V is speed of sound, Vs is speed of source, V naught speed of observer, Fa is apparent or observed frequency. F is source or true frequency. Include in learning outcome. For moving source and stationary observer, a source moves toward the stationary observer. Sketch OS. Let V directed to O. Vs in the same direction with V, thus use minus sign negative. So Fa equals to V over V minus Vs times F. Therefore, Fa greater than F. A source moves away from the stationary observer. Sketch OS. V directed to O. Vs in opposite direction with V, thus use plus sign, positive. Fa equals to V over V plus Vs times F. Therefore, Fa less than F. For moving observer and stationary source, Vs equals to 0. If an observer moves towards the stationary source, sketch OS, let V towards O. VO in opposite direction with V, thus use plus sign, positive. So Fa equals to V plus VO over V times F. Therefore, Fa greater than F. And an observer move away from the stationary source. Sketch OS, let V towards O. VO in the same direction with V, thus use minus sign, negative. So Fa equals to V minus VO over V times F. Therefore, FO less than F. Finally, note the rules of using the general equation for Doppler effect. Vs or V not in the same direction with V, which is speed of sound, therefore use negative. Vs or VO opposite direction with V, speed of sound, therefore use positive. So that's all for now. Thank you for listening. Enjoy learning physics. Bye.